Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. Andre Marie Ampere was born in 1775 in Lyon, France. He was homeschooled by his father, who was a merchant. His father directed his education and was later guillotined in 1793 during the purges of the French Revolution. Ampere, the son, taught himself Latin and mathematics at an early age so that he could understand the scientific and mathematical writings of Euler and Bernoulli. He began his academic career as a mathematics teacher in 1799 and then was appointed a professor of physics and chemistry in 1802, a professor of analysis in 1809, and then moved on to Paris, where he was a professor and chair of experimental physics. Like many other prominent figures of the French Enlightenment, Ampere's academic interests were quite broad, including astronomy and chemistry, mathematics, and philosophy. He was inspired by Hans Christian Ørsted's recent discovery of the effect of an electric current on a magnetized compass needle. So, Ampere performed a number of careful experiments on the relationship between electricity and magnetism. In fact, he is one of the fathers of the modern electromagnetic theory. The mathematical formulation of his results came to be known later as Ampere's law. This week, what I'll be doing is offering a number of lectures centered around two texts that are included in A Student's Guide to the Great Physics Texts, Volume 3. The first is from a paper titled Experiments on New Electrodynamical Phenomena. In this article, Ampere introduces some new terminology. The second is from a memoir that was presented before the French Academy of Sciences in 1820, and in this second writing are described some experiments on the force that is acting between two parallel electric currents. So you might remember when we talked about Coulomb, we talked about the force between two electrical charges. So here, Ampere is going to talk about not the force between charges, but the force between electric currents. So what he does in this first writing that begins on page 84 in the text, it's called New Names. And here he talks about terminology. So for example, he says the word electromagnetic is used to characterize phenomena produced by conducting wires of a voltaic pile. In other words, Mr. Ørsted studied the effect of an electrical current on a magnetic compass needle. The electric current was generated by a voltaic pile, and the phenomena that he was studying was referred to as an electromagnetic phenomenon. Now, what is the new terminology that Ampere is going to develop? Well, he uses the terms electrodynamic and electrostatic. Electrodynamic phenomena are any phenomena that are caused by electricity that is in motion. That is opposed to electrostatic phenomena. These are any phenomena that are caused by electricity at rest. So this is going to be an important distinction that enters the vocabulary at the time of Ampere. Now, let's move on to a second article. That was a very short first article. The second one is, again, it begins on page 84, and this article is titled On the Mutual Action of Two Electric Currents. And what he's going to be doing is talking about some experiments that he carried out where he measured the force of attraction or repulsion between two parallel current carrying wires. In fact, that's the experiment that we're going to carry out in lab this week here at Wisconsin Lutheran College. But before he talks specifically about his experiment, he wants to talk about the distinction between what he calls electric tension and electric current. So let's spend a few minutes talking about electric tension and electric current. What do we mean by electric tension? Two objects are said to be in a state of electric tension when they have different electric potential differences. So two bodies are said to be in a state of electric tension when there's an electric potential difference between them. So, as an example, if we have a battery, the two poles of the battery, the copper pole and the zinc pole, are in a state of electric tension. That is, one is positively charged, one is negatively charged, but there is no electrical current that is flowing between the positive and negative poles. It's a static phenomena. They're in a state of electric tension. How do we know when things are in a state of electric tension? It can be measured using an electrometer. So an electrometer is a device for measuring the existence of electricity, static electricity on something. So for example, if we have a positively charged sphere that's on an insulating stand, and we were to take another little positive sphere, we could determine that this is charged up by bringing this one nearby because it feels a force of repulsion. Likewise, if we had another sphere that was negatively charged and we brought this one over nearby, it would be attracted to it. So the existence of these charges can be ascertained by the attraction or repulsion of this light little body that is charged up. So this is acting as an electrometer, a way of measuring the presence of electricity on these two objects. These two objects that have different charges, positive and negative, they're differently electrified, they are said to be in a state of electric tension. They have an electric potential difference between them. This terminology of electric tension isn't used as much today as the term electric potential difference, but it still is sometimes used. So sometimes you'll hear power companies referring to high voltage wires as high tension wires. So that's just another word for high voltage. Okay, so that's two objects that are in a state of electric potential difference or electric tension. What about electric current? Well, electric current is when you have electricity in motion. So if you have a wire and you hook it up to the terminals of a battery, so one side is positive, one side is negative, and then you get electricity flowing through it, that is a state of electric current. Now, notice that when you do this, if you were to hook this up to a battery, I'll draw a little battery right here like I had when we were discussing Ørsted. So here is a battery, and you hook it up like this, you have electric current going through it. How do we know that there's an electrical current flowing through a wire? Well, you can't hold a little charged ball next to it and determine whether or not there's a current flowing through it. After all, this wire overall is neutral when there's a current flowing through it, and so you can't hold a positive charge near it and expect it to attract to it or repel from it in order to determine that there's an electrical current flowing through it. So how do we know that there's an electrical current flowing through this? Well, there are a couple of ways that Ampere mentions. First of all, he says you can measure electric current using a galvanometer. And this is essentially what Ørsted did. What is a galvanometer? It's basically a suspended compass needle. So if you were to hang a compass needle near this and the compass needle suddenly turns sideways when you're hanging the compass needle above it, that would be indicative of the presence of an electric current in this wire. So a galvanometer is a way of measuring electrical current. Notice if you hung a compass needle near this positively charged or near this negatively charged object up here, the compass needle would not turn because the compass needle does not detect the existence of charge, but it does detect the existence of charge in motion or electricity in motion. Another way you can measure the existence of electric current is using electrolysis. So let me say something about electrolysis. You can probably see electrolysis, E-L-E-C-T-R-O-L-Y-S-I-S. You see electrolysis, so using electricity to lyse or to cut something. And in particular, electricity can be used to cut water into its constituent elements, hydrogen and oxygen. Some of you may have done this in a chemistry lab experiment. So let's imagine we have a battery. Okay, so we've got a copper plate on one end and zinc on the other. So the copper is the positively charged plate and the zinc is a negatively charged plate. If we hook a couple of wires up to this and we hook each of these wires up to a metal plate, and then we take these metal plates and we dip them into a bowl or a bucket or a trough that has water in it. So we have a water-filled trough. Okay, so this is water-filled trough. And to amplify this, you can even add a little bit of salt or acid to this to amplify the effect. So what happens when you do this? Well, again, you can determine there's a current flowing through this circuit by holding a galvanometer, a compass needle, near this wire and seeing it deflect. But let's suppose you That's not the only way you can determine there's electrical current flowing in here. What you can also see is that when you do this, you'll get little bubbles that form on each of these plates and rise. So you get bubbles forming at these plates. And if you collect this gas, you will find that the plate that's hooked up to the copper terminal, you get oxygen gas that forms there. And over here, you get hydrogen gas. Okay, so what is happening here? Well, the water is undergoing electrolysis. It's getting broken apart into hydrogen ions, or H plus ions, and those move in this direction, and then they combine into H2 molecules and form hydrogen gas. And the oxygen ions move in the other direction and accumulate over here, forming oxygen gas. So in other words, the H plus, or the positive ions, move, in this case, leftward, and the O minus ions move, in this case, rightward. Okay, so the very existence of the accumulation of hydrogen and oxygen gas at those plates is indicative, Ampere says, of electrolysis, or the decomposition of water into hydrogen and oxygen gas, and that's happening because there is an electric current. Okay, and maybe I'll say one other thing about this. Notice the puzzle that this raises. Which way do we say electric current is flowing? He's going to come back to this in a couple of pages where he talks about the sense of the electric current. Because after all, should we say the current is flowing around this circuit in the clockwise direction or in the counterclockwise direction? Because the negative charges are moving to the right down here, and the positive charges are moving to the left. So there's kind of these two interpenetrating fluids of ions moving in opposite directions. So how can we unambiguously say which way the electrical current is flowing? So we'll come back to that topic next time. But first, we're going to look a little bit more carefully, along with Ampere, at the distinction between electric tension and electric current, and how electric tension can give rise to electric currents.